everyone. In this module, we're going to talk about the domain and range of a quadratic function. Just to recap on what we did in module 2, we graphed x squared, negative x squared, 2x squared, half x squared, and we also graphed x squared plus 1, x squared minus 1, x plus 1 squared, x minus 1 squared. With these functions being graphed, at the time, we mentioned that the domain and range for these functions are, they're the domain all real numbers, right? Because horizontally, these curve it's a horizontal span in both directions, from negative infinity to positive infinity. So all of these have the same domain and range. And these curve will go indefinitely in both directions. All of these indefinitely. So the domain and range can be determined by observing the graph of these curves, right? So these tendency, these arrows, and determine the horizontal span of these curves is from negative infinity to positive infinity. Domain are all the same, okay? Just like it's the same as for polynomials and quadratic function is a special case of polynomial. However, the range varies, okay? The range of x squared, 2x squared, half x squared will be the same. Their lowest point is 0, 0, and the highest point goes to infinity. And so we can say the range for all of these functions, okay, in another form, that is, okay, x squared is greater than equal to 0. Two x squared is also greater than equal to 0. And this half x squared is greater than equal to 0. Negative x squared, however, the domain is the same. And the range, however, is from negative infinity to 0. Okay, so it's from negative infinity to 0, i.e., that is negative x squared is less than equal to 0. I would like you guys to know about these inequality forms of expressing the range, okay? With that said and done, let's look at these other curves. For these three functions, okay, of course we know that we have x squared. X squared is the one in black. X squared plus 1 is the green. Which is x squared plus 1. And the red is x squared minus 1. We understand the x squared plus 1 is x squared shifted up by 1 unit, vertical shifting up. X squared minus 1 is vertical shifting down by 1 unit from x squared. So the domain are the same. Range, however, so if we make the same table about domain and range, okay? And we will have similar features, domain and range, okay, domain. Let me add another column. Okay, domain, all the same. Okay, whether we have x squared, x squared plus 1, x squared plus 1, and the next column is adding a row. So here we have x squared minus 1. Okay, I'm going to remove those. I'm going to clean this up a little bit. Okay, domain, they're all real numbers. It's all the same, from negative infinity to positive infinity. All three are the same. Range, however, are different. Here. There we go. Okay. The range for all three functions, however, the range for x squared, of course, is still x squared plus 1. X squared greater than equals to 0. For x squared plus 1, it's going to be x squared plus 1 on both sides. So that's going to be x squared plus 1 greater than equals to 1 if you work with the inequality. And if you look at the green curve, you can see that the horizontal span of this curve, it goes, this is the lowest point. This is the lowest point. The lowest point, of course, is 0, 1. This point is 0, 1. And the highest point and the lowest point, the lowest height is 1. Okay, the lowest height is 1. This is the lowest height. And the rest of the height will be higher and higher yet, higher and higher yet. Therefore, the range is x squared plus 1 greater than equals to 1. And for x squared minus 1, which is the red curve, as you can see, it's x squared minus 1. This is going to be greater than or equals to negative 1. The range in interval notation, would be, I will give you the interval notation. That's going to be from 0 to infinity. We know this. And the next one, E, that's going to be from 1 to infinity. And the last one, that is from -1 to. So these are the domain and range for these circumstances. Now, the third case we have done before, which is also considering the domain and range. If we consider the domain and range for these functions, okay, so let's recognize what are these three functions. What are these three functions? These three functions are, okay, and first of all, let me put this tables here next to it so that we can, when we work it, it doesn't cause much of shifting. Okay, and one more row. So domain, and we have three functions here. One is x squared, of course. We have rather, every two other functions are relative to x squared. And the other one is x minus 1 squared. Okay. The domain, of course, is all real. All real. There. All real. Let's look at the range. Let's look at the range. Okay. And of course, we know that x squared is the red. Wait, the x squared is the black right here. And hold on, the green is x plus 1 squared. And the red is x minus 1 squared. They all have the same domain. Range, however, range. Because the square is done outside, okay, we do x plus 1 and then squared. So the range for all three functions are going to be the same as we see from the picture. They're all greater than or equal to 0. And of course, range in interval notation are all the same as well. Okay, so from 0 to infinity. So with this review behind us, we understand these pictures. If you have any questions, go back to, please go back to module 2. To review those, review the graphing. So the domain and range for these functions. Now we can imagine if we have x plus 2 squared. So if this is turned to x plus 2 squared, the range is, domain and range is still the same. X minus 2 squared is still the same, right? For other functions, for other functions, hold on. For other functions, let me clean this up. For other functions, right? Suppose I do 3x squared, 1/3 x squared, or 5x squared, 1/4 x squared. The domain and range actually will stay the same. Will stay the same. Okay, so these examples help us to understand and the domain and range. And also in other cases, suppose we have x squared plus 1. This is plus 1. Suppose we plus 5. Then the range will be greater than equal to 5. So that was pretty straightforward, right? But anyway, so you can see that these examples will give us pictures into how to determine domain and range in a special form, in some special form. We're going to talk about that special form right now. For a general quadratic function, though, domain are all the same. Okay, domain all the same. And for example, the domain, we don't need to worry. Okay, domain is always all real numbers. All real numbers. From negative infinity to positive infinity. How about range? Range varies. But we do have some patterns. We're gonna use some examples to talk about how to determine the range of a quadratic function. There are some ways to determine. One of the popular way of doing it is by completing a square. So we're gonna talk about this method. Okay, and of course there's a formula method. There's a formula method. Formula method is, you just use the formula to determine the range. And let's talk about this more popular algebraic way to determine the range. For example, as a quadratic formula, quadratic function, general form, suppose A is 1, B is 2, C is -3. We call these three quantities parameters. When these three parameters are given and we have a quadratic function, three parameters are given, then we have a quadratic function. Three parameters are given, we have a quadratic function. Now, take the first one, for example. Okay, we want to determine the range of this quadratic function. Let's see how we do it. Okay, so we're going to do example number 1. Determine range of the quadratic function. Okay. One of the things we do, we call the technique called completing a square. Completing a square. What we do is that we're going to keep this equal, and we're going to add 1 and subtract 1. So essentially, we're adding a 0. Okay, we're adding a 0. 0 adds anything, stay the same. Okay. Any number adds 0 stays the same. Okay, so we added a 0. Why we added a 0? Okay, the 0 we have selected is by 1 plus 1 minus 1. Then why 1? Well, if you look at the following step, you will understand why it is chosen to be 1. Because when we have x squared plus 2x, these three numbers makes a perfect square. This makes a perfect square. The subtracting 1 here is to maintain the equality sign. So adding 1 to make the perfect square, subtracting 1 to maintain the equal sign. So this 3, if you factor these 3, we're going to get x plus 1 squared. And minus 1 minus 3, that's going to be minus 4. Okay, in this form, we call it x minus h squared minus plus k. Okay, and we can see that h is equals to -1, k is equals to -4. For those of you who are familiar with this form, then you can tell that the vertex is h comma k. The vertex is hk, -1, -4. Okay, so if you're familiar with this form, then you know that this parabola opens up and the lowest point is -1, -4. What it means is that with this function, we have worked out, okay, if we trim off all these other steps in the middle, and we will find that when we substitute f of x, substitute x by -1 into either form, we will get a -4. Okay, when -1 is substituted, the perfect square part is 0. Okay, so notice when x equals to -1, x plus 1 squared is 0. Okay, so from this form, we can determine that the lowest point is -1, -4. Okay, and this is the vertex. Vertex is the lowest point of this parabola. So if we graph this curve, suppose we graph using this form. How would we graph it using this form? Right? We will, if we utilize the knowledge we learned before, we first graph x squared, and from x squared, we're going to graph x plus 1 squared. Okay, from x plus 1 squared, we're going to graph x squared minus 4. Okay, so here's the step. Okay, so use what we have done before. Okay, so I'm going to bring back these 3 pictures. Okay, hopefully this will help us to see how we should shift. Okay, how should we shift? First of all, x squared. Okay, let's first graph x squared. X squared is graphed right here. Okay, we have done this graph, so we will consider this is known. And then we're going to graph x plus 1 squared. And we know from our prior knowledge, x plus 1 squared is just a shift to the left by 1 unit. So we're going to graph from here, we're going to shift to the right by 1 unit. Okay, so we're going to use the green. Okay. Green. So x plus 1 squared shifted to the left by 1 unit. There. Shift to the left by 1 unit. Let me make some adjustment here. Just make some adjustment to this range of the curve. Okay, so this is shifted left, which is this is the green is x squared, and next we're going to graph the final curve, which is shifted down by minus, this will be similar to x, so something square minus 4. So this is going to be shifted down by 4 units. Shifted down by 4 units. So now we graph the final curve. Shifted down by 4 units. So you can see the vertex ended up at a -1, positive, -1, -4. So at this point, you can see the shifting first. Everything shifted to the left by 1 unit when we shift, when we do x plus 1 squared from x squared to x plus 1 squared. So the vertex from 0, 0 to -1, 0. And then we shifted down by 4 units. So this point ended up at -1, -4. So this final point here, which is going to be -1, -1, -4. Okay, if we notice the form that we just found, right? F of -1 equals to -4. So when we plug in the -1, which is the number of units shifted horizontally in the function, and we get the lowest point. So as a result, the range is from -4 to +infinity. Okay, so let me write it down right there. Okay. So the range is from -4 -4 to positive infinity. Positive infinity. Okay, and let me give you some different forms of these, the range. And then we go on to the next example. Then we go on to the next example, which we're going to do. Okay, so the range. So f of this is a different forms. And when we talk about the range, we're really talking about this function, this function's value. Okay, this function takes different forms. These two are the same functions. And it's always going to be greater than equals to -4. So that's the meaning of the range. And this is for any real number x. Okay, so that's true for either form. Okay, to summarize in this section, that we see that to determine the range of a quadratic function, if we use the algebraic form, we do a completing a square. So we make a perfect square. Okay, we make a perfect square in the quadratic function. When the perfect square is 0, we have determined the range. We have determined the range. And that range in this case is from -4 to infinity. In the next example, we're going to look at the case when a parabola opens down.